Hello everyone, we are going to continue our discussion on the hashing, and today's topic will be universal hashing. But first, we have to finish up a few topics we didn't quite finish in the last lecture. So a very quick review first. Well, when we are doing the hashing, we are sending a key into a hash function, and then the hash function will tell us which slot of the hash table we are going to send our value to, right? So in this process, well, it is quite possible that we are going to have collisions, which means we have two keys, and then those two keys send to the same hash function, and then the hash function tells me for those two keys they belong to the same slot of the hash table. And then how are we going to solve that? So the very first way is we can do open addressing, which means, well, another name for that is called probing. This means if we want to send a key to a specific slot in the hash table, and then if this slot has already been taken, we move down and we check the next slot. And is that been taken? If yes, we move down and we check the next one. We are going to keep on check down until we find a open slot, and this is called linear probing, and this is probably the easiest probing we can do. Okay, and the next one is called chaining, which means instead of using each of the slots as one spot for one key, we open up a linked list. So if we send two keys to the same slot, and then this slot will be the head of a linked list. So key 1 sent to this slot, and then this starts a linked list, and the key 1 will be the first node, and then later we have key 4, and the key 4 comes to this node again, so key 4 will be the next node in the linked list. So well, do we still have collisions? Yes, we do. But we don't have to worry about that because there will be a linked list. So after we are sent to a specific linked list, and then we may have to insert the new node to the linked list. Or if we are doing a search, and then we have to do a sequential search on the linked list. So this is another way that we can solve the collisions. So what is the performance of chaining? So if we are doing the chaining as our solution to solve the collisions, do we still have the constant access of the data using a key? That is the part we want to pay attention to. And to answer that question, we first have to know another concept called load factor. So load factor is if we have n keys or n nodes in the hash table, and then there are a total of m slots available in the hash table, and then the load factor is n divided by m. And the point I want to remind you is, since we are doing the chaining, well, here, can we have the load factor even greater than 1? So think about this. So in this example, we have a total of 10 slots, and then we only have 1, 2, 3, 4, 5, 6, 7, 8. So we only have 8 nodes in this case. So if we want to get the load factor of this example, that is 8 divided by 10, so that is 80%, which means, well, among those, we are probably still in the okay-ish shape, right? So if we want to have more n value greater than m, can we have that? The answer is yes, since we are doing the chaining and there's no upper bound of the length of a linked list, right? So if we have 10 more nodes, and those nodes are all here in this linked list, is that doable? Of course, yes. So in this case, we will have a n value even greater than m, which means, well, the load factor in this case can be greater than 1, no problem. And what is the average cost of a n successful search with a key? So if we are considering this case, we are looking for a K20, for example. So, and for the K20, we use a hash function, and then hash function will point us to a specific slot in the hash table. And then what do? We have to visit all the nodes one by one. So for example, if our hash function says, okay, if there is a key 20, the key 20 should belong to this slot. And after that, we have to do a sequential search. We check K5, we check K2, and then K7, and then ta-da, that is already the end of the linked list. And this means we don't have the K20, right? So in this case, we have to go to a specific slot, and then on this slot, we have to do a sequential search. And what's the worst case? Since it is a unsuccessful search, we visit everything, and eventually we say, we don't have a K20 in this linked list. Okay, so what will be the average cost of a unsuccessful search? And then that is the 1 plus alpha. So where does this alpha come from? So alpha is the load factor, right? So let me draw an example here. So we have already got a linked list, and the M is 10, saying we have a total of 10 slots. And then if you count, there are 1, 2, 3, 4, 5. There are 5 values there. So N equals 5. And then if you want to check the alpha, alpha is 5 divided by 10, right? So this means on average, we have for the linked list, the average length will be 1 divided by 2. And this alpha can be considered as the average length of the linked list possible on this hash table. Okay, so with that being said, so the first step, when we have the K20, so if we have the K20, and then the first step will be we want to do a hash function K20, right? So what is that? So that is O1, because hash function should be fast enough, and that is a O1 that we can tell which slot we should do the search. And the number 2, well, remember we have to do a sequential search. So that is sequential search on a linked list. And on average, the length of the linked list will be O alpha, right? So, and then to search on a linked list with alpha as the expected length, and then this search will be O alpha. So for a search of K20, this is an unsuccessful search, and then we are going to add this part and this part together. So we got O1 plus alpha in this case. So this is a proof of why in a unsuccessful search, and then the time complexity will be O1 plus alpha. So let me come back. So the next part is, how about a successful search? So if you're searching for a value, and then this value is indeed in the hash table, and then what will this time complexity be? So this will be O1 plus alpha divided by 2. So why it is that? Okay, let me come back here. So we are discussing a successful search. So for example, we are searching for the K1. So in this case, we are looking for the K1. Okay, so for the first step, we have to do the hash function. So K1, we send K1 to the hash function. This is a constant time again. And for number 2, we have to do another search. But for this search, we know K1 is guaranteed to be somewhere in this linked list. If we are lucky, this is the first one. If we are unlucky, that is the second one, right? And then for this list, we know the expected length is alpha. So this value, the K1 we are looking for, has to be somewhere in the current linked list. And if we take the average case, we only need to search half of the linked list before we can find that. So this is the expectation, right? So for this search, well, we are expected to only search for half of the linked list to find the value we are looking for. So that is the alpha divided by 2, because alpha itself is the expected length of the current linked list. So that is, if we add those two together, we got 1 plus alpha divided by 2. So that is for a successful search. Okay? Okay, so that is the expectation of the time for a successful and the unsuccessful search. And for this one, and well, if we take the divided by 2 as a constant, we can drop that. So no matter it is a successful or unsuccessful search, the cost of a search in a training hash table will be O1 plus alpha. So the next part, well, if we got the time complexity with the alpha as a term, and the next question we want to ask is, how do we consider this alpha? Do we consider this alpha as a constant as well? So you see the blue line. So if the number of the keys in is proportional to the number of the slots in the table, which is alpha, and in this case, well, we are considering n to be a relatively small number compared with m. And then this alpha can be considered as a constant value. And when alpha is already a constant value, and then this O1 plus alpha becomes constant as well. Okay, so this means we can have a constant time search. And this is exactly what we want. However, remember, we have comparing the n, the number of the keys in the hash table, versus m, which is how many slots are available in the hash table. N has to be smaller than m, so we can have a constant time searching. Okay, so well, this is the same information and I just put them all together. So no matter it is a successful or unsuccessful search, well, the search time cost will be O1 plus a alpha. And if n is proportional to m, and then alpha can be considered as a constant time, and in this case we can have a constant time search. So before we move on, in this example, if we change the n to 50, okay, so I'm making a crazy change here. So if n is a 50, and then we will have 50 divided by 10, so we will have a 50 divided by 10, and then we will have the alpha as a 5. Oh, this is already a lot because we have only 10 slots. However, we have already got 50 items in 30. So what is alpha? It is 5, right? So in this case, alpha 1 plus O1 plus alpha will be O1 plus 5. So that will be O6. And then in this case, this is O1 plus alpha divided by 2, which is 2.5. Okay, so this is O 3.5. So in this case, my question is, can we consider this still as a constant time lookup or a constant time search? Think about that. So the answer is actually still a yes. So even though the load factor alpha is already higher than 1, and in the real world scenario, this is not recommended. However, well, in this case, well, no matter we are dealing with O6 or O3.5, they are still considered to be a constant time. So let me do something even worse. So instead of 50, we do m square. So if we change the n to m squared, and then we do have a real problem. So you can do the math again. So in this case, instead of 5, alpha will be m. So in this case, we are going to have OM here, so we end up with a linear time search instead of a constant time search. So, well, this is the point we set on this part. So if n is proportional to m, and then we can consider alpha to be a constant time. Okay, so this is for the analysis of the chaining part, and I'm gonna see you in the next video. We are gonna continue discussing how we can design a good hash function. Okay.